So then we move a little bit further forward, and where are we still? Look, we're in the 17th, 18th century. We've hardly moved in time, and along comes another major step forward. What's the major step forward? Well, two things. The one, don't sit under an apple tree, obviously. We one note that Isaac Newton will be able to tell you about. And this probably did not happen, but it always makes a good story. But the suggestion is that Newton saw an apple fall and said, the motion of that apple is the same, it's governed by the same law as the motion of the moon. Now, up till now, it's really an important point, because this is a fundamental change. And when I talk to students about laws, I can see them, and they get really bored. It's laws. But the thing I would always say, laws are amazing for two reasons. One, we don't make them. You and me don't make the laws. Secondly, our universe has laws. Neither of those things are necessarily obvious. Maybe the first one is, but the second one isn't. And I'll give you an example of a law. It's a fairly obvious one. Okay, so I'm going to let that go, and it's going to fall. That's just the way it goes. I'm going to do it again, and it does the same thing. Now, I really don't like that. Well, that's tough. Because the law of gravity has a certain way about it. And there is no way that we know of, certainly under normal circumstances, in fact under any circumstance, that we can manipulate that law. Somehow when the universe was created, gravity was created with it, but the fact that we know it's there is a huge step forward. And I'll explain to you in a second why. So, Newton said, he actually, and I remember when I went to college, we had the laws, or the universal laws, or the laws of motion, and the universal law of gravitation. I just kind of passed over this universal word. Actually, this is the amazing word in it. It's the universe. The whole universe is covered by the same laws. And we can tell that that's largely true because when you look in the universe, it looks kind of the same. Remember we said there's stars, planets, no matter where you look you see maybe more of them, but they're basically the same. The simplest way to explain that is the same laws are the same everywhere. Our Earth doesn't have special gravity laws. They're the same laws as we see elsewhere, because that explains why things are everywhere are roundy, but not quite fully round. But it also says, and one thing that Newton says, that the law that applies to apples applies to planets, applies to galaxies, and so on. That's a huge step forward. That's enormous. We've gone from a couple of thousand years previously, in fact, less than 100 years previously, into really thinking that the Earth might be the centre of the universe, into realising that not only is that not the case, but that there are laws that govern the whole universe. And these laws explain these things: big planets, smaller planets, wonderful planets. They explain big stars. Here's the sun in comparison to the planets. You can see how large the sun is to scale. And here's some galaxies. So when we look at these galaxies, this one looks different to this. This one looks very weird. This one looks also weird. But we can call it weird. Well, I'm calling it weird. Maybe you don't want to call it weird. But actually it turns out that those shapes can all be explained by the universal law of gravity. They may look very different. It's a bit like we all look different, but we're governed by DNA. It's the same thing. There's a code that the universe has underneath it that explains all those shapes. How do we know? Well, if I take Newton's laws and I try to make a model, I'm not going to do this tonight, that makes this shape or this shape, I can do it. So it's like going back to the thing we were talking about a few minutes ago, about explaining the movement of the planets and the problems with it. If we assume there's a universal law of gravity, we can explain the shapes of pretty much everything. So it's got to have some credibility across the universe. It works. And that's the beauty of having laws in the universe. Now, once you have a telescope, accelerate now, once you have a telescope, you want to make a bigger telescope. Why? Well, if you make the bigger telescope, then two things happen. First of all, you can see more detail, you can magnify more, and secondly, you can see fainter objects. And if you can see fainter objects, you've got the possibility of seeing things that are farther away. Come back to that in just 1 second. But if you've never visited Birr Castle, and if you've never seen this telescope, then you got to do that also. So you got to go to Newgrange. These are orders. You have to get your dad to bring you, by the way, now if he hasn't done that, okay? So you got to go also to see this. This was the largest telescope in the world for 70 years. It was built in Birr in County Offaly, which hasn't changed very much since this was completed in 1845. It wasn't built in a metropolis. Interestingly, around the same time, there was a reflector built in the small city of San Francisco. Interesting to see the difference in developmental path between Birr and San Francisco. I just always think that's an interesting because one had the largest telescope with a mirror, which is in Birr. One had the largest telescope with the lens, which was in San Francisco. And the third Earl of Ross, who lived there, saw this galaxy, and he called it, and it was called by others, a nebula. A nebula means cloud. And it's actually because we don't know what it is, so we're going to call it nebula. That's it's a cover-all word. And the big issue was, how far away is this? So, looking at it, can you tell how far away it is? I mean, obviously it's 10 feet away from you, or 20 feet, but the real thing. And you can't. And actually, here's the thing. The next time a person says, I saw a UFO last night, and it was 50 feet long, or, 20 meters long, and it was 400 meters away. And it's amazing. I used to be interested in UFOs a bit more when I was younger. Amazing how people will say they think they know the scale of something. Now, the only way you know that, you could have some idea how far away I am, because you kind of know inherently how big people are, roughly. So, but if it's a UFO, you have no idea how big it is, so you have no idea how far away it is. So if you have no idea how big this is, you have no idea how far away it is. And if you have no idea how far away it is, you don't know how big it is. It's a circular problem. So something somewhere has to unlock this. But there was a big debate about this. And here's the reason why this was really important. People back at this time, in 1845, and right into 1900s, right in 1910, actually up until 1921, didn't know how big the universe was. So we didn't know how big that was. So the big challenge was to measure the size of the universe. A lot of very smart people saying it's small, it's big, it's small, it's big. And this is where these stars and nebulae, how far away are they? Well, for those of you who remember Father Ted, you'll remember Father, what's his name? Dougal. Trying to explain how far away the cow is. Okay. So, and for those of you who aren't so familiar with it, obviously a cow in a field is far away, or a model cow is close up. And of course, this becomes impossible for Dougal to understand in the story, and it's very funny. But actually, this fundamentally tells us the problem in astronomy, because we don't know how big the cows in the universe are. Now, well, at least we didn't. We figured that out. So, in essence, if you can find something whose size you know, or whose brightness you know, and you place it at different distances, then you can tell how far away it is from how big it appears or how bright it appears. Does that make some sense? So once you know the size of something, if it appears very small, you can figure out how far it is away. If you know how bright it is, you can figure out how far it is away just by measuring how bright it actually appears. So we got to find things whose size we know in the universe. And in fact, there are such things. I'm not going to go into it tonight, you'll be glad to hear, because you'll be thinking, this guy needs to not talk all night. But they're called primary distance indicators. And there's a couple of different things that we know the size of through measurements, which I don't really like when people say just take it on faith, but just take it on faith for in the purpose of tonight's talk.